shared few recordings. Yesterday I uploaded one recording on analysis of doubly beams to our recording, and the previous recordings on design of beams to our recordings, and with your section also on 19th May recordings are present in the folder. So are you following the recorded lectures? So have you gone through the recorded video? Let me just point out this one, design of beams, and then analysis of beams. And with your section, the recordings on 19th May 2 are present here. So have you seen them? So please raise your hands, those who have watched design of beams recording uploaded on 18th of May. This one highlighted. हाँ जी, किसी अल्लाह के बंदे ने देखी है ये मूवी 2 आवर्स की, या किसी अल्लाह के बंदे ने ये मूवी देखी हो? येस्टरडे को मैंने अपलोड की. Or the one recorded with your sections uploaded on 19th May, which is also on the topic load transferred on beams. So can you raise your hands, those who have watched these videos? So if you are not watching these recorded lectures, then how can you prepare this subject for exam, mid or end term? So I have uploaded yesterday a recording on new topic, analysis of doubly beams, which I want to discuss today, this one, but its 2-hour recording is already present in your Teams folder, and today I only have 1 hour with you, but you can get complete 2 hours recording in your folder. I discussed with you load transferred on beams and then design on beams, and I mentioned that in next lecture we will discuss bar bending schedule, but actually in bar bending schedule, which finally helps us to estimate the steel weight which will be used for the project, for cost analysis, and even for the final steel fabrication and layout, that schedule is very important. But the example which I shared on the materials folder, which is the PDF file, there is one example given for calculations of steel weight. You will find in that example not only flexural steel, the shear rings are also provided, estimation of the weight of shear stirrups. So actually our other topics are shear design of beams, and then slab analysis and design, and the leftover beams are doubly reinforced beams, and then in terms of geometry, T-shaped or L-shaped beams. So once I will finish all these members, flexural and finally the shear design, then I wish to discuss with you the bar bending schedule and estimation of steel weight. Because in that example, there are other reinforcements which are not taught yet, like shear stirrups. So I today want to discuss doubly reinforced beam, and its recording is already present. So I will also record today's 1 hour lecture. So we are only left with around 40 minutes. So I recommend you to also watch 2 hour recordings present in your folder. So our topic, very important one, is doubly reinforced beams. So beams having both tension and compression reinforcement to allow the depth of the beam to be lesser than the minimum depth required for singly reinforced beam will result into a doubly reinforced beam, like this section is shown to you. For example, if there are 3 bars on the tension side, I may draw tentative location of neutral axis. So if neutral axis is somewhere over here and there are cracks at ultimate, for example, if we are locating this neutral axis position, on the tension side bars are present, and even on the compression side bars are present, and depth of this beam will be shallow than the depth which we actually calculate for singly reinforced beams, what we have studied up till now, whether it was allowable stress design or ultimate stand design. In ultimate stand design, I have derived one equation for d minimum, and that d minimum equation we use to fix the depth of the beam. That equation was mu over 0.205 fc prime into bw. So based on this equation, we fix the d value. Also, we examine the serviceability requirement, and out of 2, the governing will be, which will give us tension controlled under reinforced behavior, and we studied that this d minimum equation will help us to design the ductile beam. And if suppose due to architectural considerations you are not allowed to go deep in the web depth, so you are asked to finish the beam within a shallow edge, which obviously will fulfill the serviceability requirement, but it is not fulfilling this the minimum requirement. For example, if serviceability requirement is span by 20 and the minimum is span by 12, so it means you are asked to finish the beam within span by maximum span by 16. So it means now your H is, rather than span by 12, it is span by 16. Obviously, it is deeper than span by 20. So serviceability wise, it is okay, but in terms of singly reinforced tension controlled beam with epsilon s greater than 0.005, when concrete will crush, it is not okay. So in such cases, when you are required to design a flexural member with H less than the required for singly reinforced tension controlled beam, then you have no other option except to provide also steel on the compression side and then to get additional couple between steel and steel. So tension steel will make a couple with the compression steel, and also tension steel will make a couple with the compression concrete. So then T has two components. I may split up theoretically this T into two components, T1 and T2. So I may say T1 is making equilibrium with C, which is concrete compressive force, and T2 is making equilibrium with compression force developed by the steel on the compression side. So such beams are called doubly reinforced beams, and such beams in which D is less than D minimum. So I can sketch this like I will show up to the depth of the steel that this available D is less than D minimum. So we will go for the doubly beam design. So it is mentioned here, beams having both tension and compression reinforcement to allow the depth of the beam to be lesser than minimum depth required for singly beam. So it means by using lesser depth, the lever arm reduces because D minus A by 2 for the couple between steel and concrete. Once D is reduced, your lever arm will also reduce. So your internal movement resistance will also reduce. So that will be compensated by more area, and area which is present now on the compression side as well. So additional couple we will get between steel and steel. So once we are adding steel also on the compression side, we are increasing the cost because steel is costly as compared with concrete. So we can say comparatively, doubly beams are costly because steel weight or steel area is more. However, advantage is that ductility of doubly beam is more than singly reinforced beam if properly designed, ductile doubly beams. So with ductility
Excuse me,
will be,
sir.
yes please.
सर क्या स्लैब डबल रिइंफोर्स हो सकती है स्लैब?
जी जब हम स्लैब पे जाएंगे then you can ask this question. Yes, it can be. It
Okay.
can be. Ductility will be increased by providing compression steel, and in this way uh, once you will be able to perform test on the beam specimens in your lab portion, you will compare the load deflection curve of singly beams and over reinforced singly beams and then doubly reinforced singly beams. Over there you will examine that the area under load deflection curve of the doubly beam is more than even the singly reinforced beam. So compression steel obviously will provide us more energy absorption, Hanger bars, which are even used in single beams on the compression side, actually to hang the ties, to hang the shear stirrups, can be used as compression steel in doubly beams, because even in doubly beam, if it is simply supported, so it means there is no tension on the top, and the top bar is just to hang the ties. So it means the hanger bars, which are always present to hang the stirrups, even in simply supported beams where tension will never come on top, such additional steel, which is present as hanger, can participate in the compression force development. So, as a matter of fact, its involvement in compression force generation can reduce the area required for the doubly reinforced compression steel, and hence some cost can be reduced. So if we are performing analysis and we realize that the hanger bars can participate in compression force development, so we can use them as the compression steel, and in this way we can reduce some of the cost. But in that case, we cannot curtail that hanger bar even in that portion where ties are not present, because we need to develop that CC. If beam is simply supported and mid span cross section is important, so in the mid region shear force will be negligible, but we need to provide the compression force, so still the area on the compression side near the mid should be present to develop the CS. So in this way, we must be careful that if we are using hanger bars as the compression steel, it must be present throughout. Rather, we are just looking at the presence where we need to hang the ties, because here is more near the supports, but movement will be more near the midspan. In addition, for high-rise buildings, extra cost of the shallow, deep beams is offset by saving due to less story height. So in the first bullet, I mentioned that the doubly beams are costly because steel required is more. But you can imagine that if the beams are singly and you need the beam depth 1 meter and you need the clear story height 3 meter, it means then you need a total story height of the floor 3 plus 1 4 meter. And if there are some restrictions above road level that you can't go more than suppose 50 meters above the road level, you can divide that 50 with 4 and you will get number of floors what you can add. But in case of doubly beam, if you can finish the beam within 0.5 meter, it means your clear story requirement from architect was 3 meter, 0.5 is your beam. So total it will become 3.5. So it means 50 divided by 3.5 will give you number of floors what you can add above road level. So in this way, in case of shallow beams, you can get more number of floors, and in this way long term you can obviously judge that with a building with more number of floors will give you more uh, reward in terms of sale, purchase, or in terms of rent, rather than a building which has less number of stories. So it is normally preferred to have the more floors, especially when the land cost is very high in commercial areas. In compression steel may reduce presence of compression steel in doubly beam. The other advantage is, you know that concrete is prone to creep and shrinkage, and it will increase the long-term deflections, and it will be a big, it is a big demerit of concrete. If the steel bars are present on the compression side, it means some of the volume of concrete is replaced with the steel, and hence you will be able to reduce long-term deflections if you are providing doubly beams, because the creep and shrinkage in compression uh, zone of the concrete beam will be reduced because steel is present there, and some of the area of the concrete in section and in the element in terms of total volume of concrete is reduced. Use of doubly reinforced section has been reduced. It means application of doubly beam after this introduction of ultimate stand design, which fully utilizes the concrete compressive strength. It is just one comment that earlier when there was ASD in practice, allowable stress design, we stress the concrete up to 45% of FC prime, and then we designed at service loads. Now, since in ultimate stand design, we are using the complete area under the concrete, so up to 85% of its peak. So as a matter of fact, the C force calculation is now under the complete area of the concrete. So it is stated that with ultimate stand design, we can develop a reasonable CC compression force with concrete alone. So as such, the introduction of additional steel to develop a couple may be little needless, but it is just one observation or comment. But still, when you are going uh, low in height as compared to D minimum required, and also concrete strength is not too high, you have to go for the doubly beam design. You need to provide some bars in the compression domain to handle the uh, additional couple, to provide the additional couple. Now, in terms of doubly reinforced beam classification, there are two types of doubly reinforced beams. Uh, there are case 1 and case 2 doubly beams. Just give me one second. Okay, let me continue. In terms of doubly beam classification, there are two types of doubly beams. Like in singly beams, we mentioned that singly beams are under reinforced singly beams, they are transition reinforced singly beams, or they are over reinforced singly beams. Similarly, even in doubly beams, we will design the doubly beams tension controlled under reinforced. We want the tension steel in doubly beam above 0.005. But if it is in between 0.005 and epsilon y, so if they are transition reinforced doubly beam, still they are under reinforced acceptable. But over reinforced doubly beam is objectionable. It is not preferred, or it is, you can say, not allowed to design over reinforced doubly beam, just like a singly over reinforced beam, doubly reinforced, uh, doubly over reinforced beam is also dangerous because it will give us brittle warning. So it is mentioned with the red color underlined that tension steel will always yield in under reinforced doubly beam. So then question will arise, what is the classification then? In doubly beam, there is one more puzzle, and that is, what is the status of compression steel at ultimate? So there are two cases in doubly beam. We are not taking into account we are not puzzled actually regarding the tension steel. Regarding tension steel, our requirement is still same. It must yield excessively at ultimate when concrete will crush. But corresponding to that, what is the status of compression steel? So there are two cases then in doubly beam. Case one, very ideal, that compression steel is also yielding at ultimate. So it means tension steel is yielding, compression is also at yield at ultimate. Simple to analyze and very easy to get the capacity of such beams. Case 2 is that compression steel at ultimate is not yielding. Still acceptable because in terms of ductility, in terms of selection of phi for capacity reduction, compression steel strain is not a major concern for us. Tension steel strain warning is important. Compression steel, if it is at yield at ultimate, well and good. Even if it is below yield and is close to yield at ultimate, it is still well and good if the tension steel has given us lot of warning. So even in doubly beam, the point of importance is that tension steel yielding and to check the status of compression steel because we need to make additional couple between steel and steel. So knowing its force, its stress level, we can determine the force and then we can get the internal capacity. So both cases are very important. Case one is little simple and two requires little more calculations to establish the Fs prime. So now this slide is just like the slide which we already have uh, prepared when we were discussing the singly beams. So the only difference in this slide is if you compare it with the singly beam slides, what we discussed over there, that section from section the strain diagram, plane section remain plane, linear strain diagram, from strain the stress diagram, from stress the force diagram, and then the force, knowing the corresponding lever arms, we get the internal capacity. So there is absolutely no difference, and rather than the actual stress diagram, we have shown the simplified Whitney's proposed stress diagram on the compression side. The only difference you will find is that there is one additional material on the compression side and its corresponding strain epsilon s prime and multiplied with the modes of elasticity its corresponding stress fs prime and multiplied by area of steel on the compression side its corresponding cs fs prime into as. Its force cs is shown on the force diagram, internal force diagram. So the internal lever arm will be then between steel and steel d minus d prime, because in this picture we have mentioned that the compression steel distance from top compression edge will be at d prime. So the lever arm between the steel and steel will be effective depth minus d prime, and the lever arm between tension steel and concrete will remain the same, which is d minus a by 2, because cc will be applied at the same point, which is at a by 2. And in this way we can write based on two cases intelligently that if it is a case 1 doubly beam, then CS will be area of steel at yield. If it is case 2 doubly beam, then CS will be area of steel in compression. We are putting a prime superscript to signify that it is the compression steel, and on effective depth we are putting on the D, which is used for effective depth, we are putting a prime on top to differentiate that it is the distance of the compression steel from top. So don't forget to put prime on top. So it is actually case 2 means that compression steel is not at yield, so it may be at some lower stress value. So whatever is the stress into area will give us case 2. And in terms of CC, there is absolutely no difference. We are using uniform stress on the cross-sectional area A into B, and we know A is equal to beta 1 C. So that equation for relationship between neutral axis depth and uniform stress block depth will remain the same. So this is further explained here that in case of case 1, since epsilon s will be actually epsilon y, so fs will become fy. So if I have epsilon s prime equal to epsilon y, because steel has the same yield strain in tension and compression, it has same modes of elasticity. So if it will be on the compression side at yield, as per ultimate strength design, the maximum stress what we are going to use will be Fy. So we can't use the stress more than that. We can put prime on top, whether to put prime or not, or no prime, but it means the stress will remain maximum up to yield stress. So if the strain is below yield strain, then obviously we will have the stress value equal to some stress which is below Fy. So that we want to explore. On the tension side, there is absolutely no ambiguity that tension steel must be at yield, because otherwise we will get a over reinforced doubly beam which is unacceptable, and we are not going to design such beams. So even in case of doubly beam, the question remains the same, whether it is case 1 or case 2, that where is neutral axis. So when we are analyzing the doubly beam, just like singly, the question is where is neutral axis. In singly beam, the equation was T equal to Cc. Now we have the presence of two materials on the compression side. It is a composite of concrete and steel. So actually the total tension steel will make equilibrium on the cross section with Cc plus Cs. And since we are now writing the equation for case 1 doubly beam, so we have no objection to put the compression steel at yield, and there is absolutely no doubt that tension steel at yield. So in our equilibrium equation, the second component Cs is new, and when I expand this Cs, I substitute it is As prime into Fs prime, and since we are having case 1, so it means Fs prime is equal to Fy. So if you are performing a analysis and you are given with the cross section, so in my recorded lecture you will find a very detailed discussion from this slide onward. Let me just draw the sketch so that later on when you will watch the video of 2-hour recording, you will get good idea to understand the discussion from this slide onward. Suppose you have a beam of 300 millimeter width, and it is also deep 300 millimeter. and it has 4 bars, standard US bars of dia 25 in one layer, and it has 2 bars of dia number 19 on compression side, 19 millimeter dia on this side, and number 25 on this side. And it is mentioned on the drawing that the concrete used in this beam is of grade 20 megapascal, and steel bars used are of grade 300. If this is the information provided on the sketch, and you are asked to give the capacity of this beam, we are performing capacity analysis that this beam can support how much load or movement. If the beam is simply supported, then maximum movement at the midspan WL square by 8, or how much is the load, which is W. So if this is a question, we did the same kind of question analysis for the singly beam. Now, if only this question is provided to you without any statement that it is singly or doubly beam, just cross section with the information is given, the first hint will be why 2 number 19 are present on top. Why not 2 number 6 or 2 number 10 lowest dia if they are being used for the hanging purpose to hang the ties? Why the area given is unusually high? Second is, it seems that the beam has the depth 300 and width 300. Even if you know the span of the beam is suppose 6 meter or 7 meter, that will also give you one, you can say, hint that why for this span D minimum is not provided. So you can check even the serviceability requirements. That will also give you idea that your depth is very close to serviceability, little above serviceability. You can't go below serviceability because to go below serviceability needs some extra assessment. You must defend then that why you are going below serviceability. If you have some sound calculations which can prove that a given depth will fulfill the deflection requirements, crack widths will be minimum at service loads, then you may be allowed to go with the depth even below recommended by the code. Otherwise, even in doubly beams, you can't go below serviceability requirements. And the table I shared with you, that will remain valid. But if suppose you have all the information and this sketch is given to you with steel on the compression side as well as the depth which is not very deep, the first thing which will come to your mind is that it is probably a doubly beam. And then if it is a doubly beam, the first, you can say, step will be that you will start assuming it is case 1 doubly beam. And if you will assume it is case 1 doubly beam, you will write this equation of equilibrium to check what is the uniform stress block depth and then to get its neutral axis depth. So if it is proved later on that it was a case 1 doubly beam and it neutral axis depth is in hand now, you can very quickly calculate its internal capacity. So that is the very quick method to calculate capacity of doubly beams. Like for singly, we did the same practice. But if you write this equation of case 1 and you get A and then C And once you confirm that both steels as assumed in this equation are at yield, you got the idea that no, with this neutral axis depth, compression steel can't yield. Then it means you will discard your calculations and you will rewrite this equation by changing this Fy with Fs prime, and you will recalculate the A and then C to get the neutral axis depth for case 2WB, and then you will get the internal capacity. In that 2-hour recording, I have done this calculation for case 2. I have taken this example, and you will find in that video that this beam tells us that this is not case 1, it is case 2WB. Then accordingly, we revised our calculations and we did the reanalysis of the neutral axis depth, and then we got the capacity. So please watch that recorded video, and in next week in 2-hour lecture we can discuss some questions if you will raise after watching that video, that whether you got all the information provided in that or you are confused regarding the contents. So let me stop here recording of today's lecture. Now if you have any question, you are welcome. This recording is being uploaded in your folder. You will get this recording after a few seconds.
Sir, I have a request.
Yes, please.
Sir, I am not added in the teams.
I am. You are not added in the
Team of the PRC1.
What is your roll number?
2017 or 2015 784.
Let just hold on. In which section you want to add?
Section B.
Section B.
I have registered the subject.
You registered the subject.
In section B.
In section B. Just
Yes,
just repeat your roll number.
2017
17
R
capital R
717 R
R
2015 784.
2015. This is
Civil 84.
This one. It is visible at the moment. Only 84. This one,
Yes,
are you looking at my screen?
Yes, sir, I'm looking at it.
So now you have been added. There is no message that you can't be registered. Now you are registered in section B.
Sir,
I hope, yes.
will I receive the email?
Now you will receive the email and you will be having full access on this files folder. So
Okay,
if
sir.
I will check your, you can say registration, you will be now in this section B.
Okay, sir. And what about the? Okay, sir.
You will be able to download all the previous recordings or the class material.
Okay,
So
sir.
this
Thank you very
is,
much.
we have now 53 members in this section B. So hopefully you are one of them.
Okay, sir.
2017 or now you are there. You will get that. So any other question from your side? Query or question? Section B. So I repeat that chapter 3 solved unsolved problems, and chapter 4, I am just searching this book. It is available online, 3rd edition. So in chapter 4 all solved unsolved problems of shallow beams. This one on page 119, you need to attempt them. Shallow, this one, and doubly reinforced beams. Please attempt all solved unsolved problems in SI system of units. So they are part of your homework. So I will ask you to submit hard form once you will be on campus. So be ready. Uh, keep preparing. Keep solving the questions on the maybe on loose pages or on register. So if later on I will give you some deadline for submission, you can submit chapter 3 and chapter 4 solved and unsolved problems. Agreed?
Agreed, sir.
Okay, then if you have no other question, let me end the meeting.
So, sir, I have received the email.
Okay, good, good. Okay, then.
Thank you very much, sir. Allah
Welcome.
Hafiz.
Allah Hafiz.